Hi, everyone. I'm Evan, and welcome to Lesson 11 of National AI Youth Council's Education Curriculum, AI and Computer Vision Models. So far, we have covered numerous AI topics progressing from foundational machine learning and deep learning concepts to the critical, ethical, and governance challenges it presents. It explored AI's potential for social good and ethical development while also outlining career paths and emphasizing youth advocacy in responsible AI implementation. So, the main goal of today's lesson is to gain a comprehensive overview of AI and computer vision models. We will break this down into four key sections: fundamentals of computer vision, AI core computer vision tasks, model architectures and techniques, and lastly but not least, application and future trends. By the end of this lesson, you'll have an understanding of the key principles and techniques behind AI in computer vision models and their wide-ranging applications. So, let's dive right in. First, we'll have a warm-up activity. So, think about your daily life. Where do you encounter computer vision or AI systems already? Think about all the technology you interact with, from your phones and computers to apps and even things you see in the real world. Consider how machines might be seeing and interpreting the world around you. Take a moment to pause and reflect. Where do you encounter computer vision or AI systems already? Go ahead and pause the video right now to write down some ideas, and we'll talk about them in a moment. All right, let's discuss some possible answers. One very common place is social media. Think about features like facial recognition for tagging friends in photos or content filtering that identifies inappropriate images or videos. These platforms use computer vision to analyze images and videos you and others upload. Another example is your smartphones. Many phones have camera features that use computer vision, like automatically focusing on faces, scene detection to optimize camera setting, or even augmented reality apps that overlay digital information onto the real world as seen through your camera. And lastly, consider security systems. Many security cameras and systems use computer vision for things like motion detection, automatically identifying license plates, or even advanced facial recognition for access control or surveillance. All right, now that you've answered this question, let's get into our lesson for today. So, topic 1, the fundamentals of computer vision and AI. So, at its core, computer vision is a dynamic and rapidly evolving field within artificial intelligence that seeks to equip computers with remarkable ability to interpret and derive meaningful insights from the visual world, mirroring the sophistication of human vision. Imagine enabling machines to see in a way that goes far beyond simply capturing pixels. It's about understanding the content, context, and relationships within images and videos. The primary goal is to automate and surpass tasks that the human visual system effortlessly performs, such as recognizing objects, discerning scenes, tracking motion, and even understanding emotions conveyed through facial expression. This capability is not just theoretical. Computer vision is already profoundly impacting industries across the spectrum, from, from revolutionizing healthcare through advanced medical image analysis for faster and more accurate diagnosis to powering the autonomous vehicles that promise to reshape transportation and optimizing manufacturing processes through automated quality control. Computer vision is a transformative force with far reaching implications for our future. So, this is a picture of Waymo's autonomous driving vehicle. It can be seen on the streets of major cities in the US already, like San Francisco, Atlanta, and more. So, now, to truly appreciate the power of modern computer vision, we must understand the pivotal role of artificial intelligence, particularly machine learning and deep learning. AI is not merely an adjunct to computer vision, it is the very engine that drives its current advancements. Unlike earlier rule based approaches that relied on explicitly programmed instructions, modern computer vision models leverage the power of AI to directly from vast amounts of data. Learn directly from vast amounts of data. Machine learning algorithms, and especially deep learning architectures like convolutional neural networks, are trained on massive data sets of images and videos. This training process allows these models to automatically extract intricate visual features, recognize complex patterns, and establish nuanced relationships within the visual data, all without explicit human coding of rules. This data-driven approach is what enables AI-powered computer vision to surpass the limitations of traditional methods, achieving unprecedented accuracy and adaptability in handling the inherent variability of and complexity of real-world visual information. The deep learning revolution has truly unlocked the power of computer vision, making it a practical and transformative technology across numerous domains. To fully grasp the significance of today's AI-driven computer vision, it's insightful to trace its historical journey. In the early decades from the 1960s through the 1980s, computer vision was largely characterized by rule-based systems. Researchers attempted to manually define rules and algorithms for tasks like edge detection and basic shape recognition. However, these systems proved brittle and struggled to generalize beyond highly controlled environments. The 1990s and 2000s marked a crucial shift towards machine learning methodologies. Statistical methods and feature engineering techniques such as scale invariant feature transform, SIFT for short, and the histogram of oriented gradients, or HOG for short, emerged, leading to noticeable improvements in performance and robustness. Yet, it was the deep learning breakthrough in 2010s that truly revolutionized the field. The ImageNet Large-Scale Visual Recognition Challenge, along with development of convolutional neural networks, CNNs, and the increasing ability or availability of massive image datasets and affordable computing power, especially GPUs, acted as a catalyst. This era witnessed unprecedented surge in accuracy and compatibility, propelling computer vision into the mainstream. Today, we stand in a dynamic and exciting era characterized by the pursuit of increasingly sophisticated architectures and the proliferation of real-time applications that demand immediate visual processing and a growing societal awareness that necessitates a strong focus on model robustness, generalization to diverse and unseen data, and the critical ethical considerations surrounding the deployment of such powerful visual intelligence. So let's move on to core computer vision tasks. Let's now delve into the fundamental tasks that define the field of computer vision, beginning with image classification. At its most basic, image classification is about endowing a computer with the ability to categorize images. The core task is to assign a single representative label to an entire image, effectively summarizing its primary visual content. Think of it as answering the fundamental question: out of a predefined set of categories, which one best describes the dominant subject or scene in this picture? Consider everyday examples. An algorithm classifying a photograph as containing a cat, dog, car, or airplane. However, the applications extend far beyond simple object recognition. In specialized domains like medical image analysis, image classification plays a critical role in diagnostic processes. For instance, distinguishing between benign and malignant tumors in medical scans based on subtle visual cues. The output of a typical image classification model is a probability distribution across all the possible classes it has been trained to recognize. This distribution indicates the model's confidence level for each class, and the class with the highest probability is declared as the model's predicted label for the input image. Convolutional neural networks have become the dominant architectural choice for image classification, with pioneering models like AlexNet, VGG, and ResNet serving as foundational benchmarks and continuing to inspire ongoing advancements in the field. Building upon image classification, we encounter object detection, a task that demands a more intricate level of visual understanding. Object detection transcends simple categorization by requiring the system to not only identify the types of objects present within an image, but also to precisely localize each object. This means the algorithm must determine both what objects are present and where they are situated within the visual scene. The output from an object detection model is richer and more informative than simple classification. It typically comprises of a set of bounding boxes, which are rectangular outlines, meticulously drawn around each detected object in the image. Crucially, each bounding box is accompanied by a class label specifying the type of object enclosed within. For example, labeling a box as car, person, traffic light, or bicycle. The applications of object detection are incredibly diverse and impactful. It is absolutely essential for autonomous driving, enabling vehicles to perceive and react to their surroundings by detecting other vehicles, pedestrians, cyclists, and traffic signals. Beyond autonomous vehicles, object detection is vital for enhancing security surveillance systems by automatically identifying potential threats or anomalies, and it empowers robots to interact intelligently with their environment by recognizing and manipulating objects. Several sophisticated object detection architectures have emerged, each with its own strengths and trade-offs. Prominent examples include YOLO, known for its speed and efficiency, SSD, which is single-shot multi-box detector, which balances speed and accuracy, and faster RCNN, which is faster region-based convolutional neural networks, which prioritizes accuracy and robustness. For the most detailed and nuanced understanding of image content, we turn to image segmentation. This task represents a significant leap in visual comprehension, aiming to partition an image into semantically meaningful regions or segments at the most granular level, the pixel level. Instead of just identifying objects with bounding boxes, image segmentation seeks to delineate the precise boundaries of objects and regions, assigning a category label to every single pixel in the image. There are two primary variations of image segmentation, each serving different purposes: semantic segmentation and instance segmentation. Semantic segmentation focuses on labeling each pixel according to its semantic class, such as road, sky, building, vegetation, or person. It groups together all pixels that belong to the same category, effectively creating a pixel-wise classification map of the scene. Instance segmentation is a more challenging and refined task that builds upon semantic segmentation. It not only labels pixels by class, but also distinguishes between individual instances of the same object class. For example, an image containing multiple cars, instance segmentation would generate a separate, distinct masks for each individual car, allowing the system to differentiate between car instance 1 and car instance 2. The application of image segmentation are incredibly impactful in the domain requiring precise visual analysis. In medical image analysis, it is crucial for segmenting organs, tumors, lesions, and other anatomical structures, aiding in diagnosis, treatment planning, and surgical guidance. For autonomous driving, detailed road scene understanding through segmentation is essential for navigation, path planning, and ensuring safety. Image segmentation also finds applications in advanced image editing, enabling selective modifications to specific regions of an image, and in scenes parsing for virtual reality and augmented reality environments, creating immersive and interactive visual experiences. Key architectures in image segmentation include U-Net, renowned for its effectiveness in biomedical image segmentation, and its encoder-decoder structure, and DeepLab, widely recognized for its state-of-the-art performance in semantic segmentation tasks. Another key thing of note is Meta's Segment Anything API, which builds upon this. So this is an image to show what image segmentation does. So as you can see, there are many boxes of different colors that classifies images and segments them and gives them label them with a number from 1 through like 20 something. Activity time. Now that we've gone through this information, let's do a quick activity on computer vision. So for this activity, you'll read 6 different scenarios describing how computer vision might be used. Your task is to identify which of these 3 core computer vision tasks we discussed: image classification, object detection, or image segmentation is most likely being employed in each scenario. Take a look at the instructions on the slide. You need to determine the primary goal of the computer vision system in each case and match it to the correct task. Go ahead and pause the video now to complete the activity. Take your time to read each scenario carefully and decide which tasks fit best. We'll go through the answers once you're done. All right, now that you had the chance to think about it, let's go through the answers and more importantly, the explanations behind them to ensure a solid understanding. So for the first scenario, a system in a grocery store automatically identifying an apple, banana, or orange is primarily an example of image classification. The core goal of the system is to categorize the entire object being held by the shopper into one of the three specific fruit categories. While there might be some preliminary steps involving isolating the object, the main task is to assign a single label to the image of the fruit. The system isn't necessarily concerned with the exact location of the fruit in the frame or its precise pixel boundaries, but rather what the overall object is. The second scenario, where a self-driving car identifies all cars, pedestrians, and traffic lights on the road, clearly demonstrates object detection. The car needs to perform more than just recognizing the presence of these objects. It must also determine their precise location within the car's visual field. This localization, typically achieved by drawing bounding boxes around each detected object, is absolutely crucial for the car to navigate safely and make informed decisions about its movement and interact with its surroundings effectively. Simple image classification wouldn't provide the necessary spatial information to the car's control system. The third scenario, where a medical tool highlights the precise boundaries of a tumor in an MRI scan, is a perfect example of image segmentation. The key here is the emphasis on highlighting the precise boundaries at the pixel level. This task goes beyond simply detecting the presence of tumor, which could be done with classification or a rough bounding box from object detection. It requires delineating the exact region occupied by the tumor, separating from surrounding healthy tissue. This detailed pixel-wise understanding is often essential for accurate diagnosis, treatment planning, and for monitoring changes in the tumor's size and shape over time. The fourth scenario, where an app on your phone tells you if a picture you took of a cat or a dog, is another straightforward example of image classification. The primary purpose of the app is to analyze the entire image and assign it to one or two of possible categories, cat or dog. The app is not designed to locate the animal within the image with a bounding box. That would be object detection. Or to outline its precise shape, which would be segmentation, but to simply classify the overall content of the picture. The fifth scenario, where a security system draws a box around any people entering a restricted zone, is a clear illustration of object detection. The security system needs to not only recognize that a person is present in the camera's view, but also to pinpoint their location. Drawing bounding boxes around the detected individuals allows security personnel to know not just that someone is there, but also their specific position within the monitored area. Image classification alone would also indicate if a person is generally in the scene without providing their spatial coordinates. Finally, the sixth scenario, where image editing software allows you to select and change the color of only the sky in a photograph, utilizes image segmentation. To enable the users to change the color of just the sky, the software must first accurately identify and isolate all pixels that constitute the sky in the image. This process of identifying and separating specific regions at pixel level is precisely what image segmentation achieves. Image classification would only tell you that the image contains a sky, and object detection might provide a rough bounding box around the sky. But it wouldn't offer the precise pixel level selection needed for targeted color editing. Alright, now that you have completed the activity, here are a couple of things you should have learned or thought about. You should have recognized the image classification is used when the goal is to label the entire image in a single category, like identifying a type of fruit or animal. You should have identified object detection when the system needs to find and locate specific objects within an image, often drawing bounding boxes around them, as seen in the self-driving car and security system example. And finally, you should have understood that image segmentation is necessary when you need a detailed pixel level understanding of the image, allowing you to precisely outline objects or regions, like tumor in the MRI scan, or selecting the sky in the image editing software. Now, let's get back into some more content. So next we'll be going over applications and future trends. Okay, so next we'll be going over model architectures and techniques. So now let's dive into architectural heart of modern computer vision, convolutional neural networks, or CNNs for short. These neural networks are not just another algorithm, they are the very bedrock upon which the vast majority of successful and impactful computer vision applications are constructed today. CNNs are specifically designed to process image data with remarkable efficiency and effectiveness, mimicking the hierarchical processing of the visual cortex in the human brain. The fundamental building blocks of CNNs are convolutional layers. These layers act as trainable feature extractors. They operate by sliding small matrices, known as convolutional filters or kernels, across the input image. As these filters convolve around across the image, they detect specific local patterns or features such as edges, corners, textures, and basic shapes. Each filter is designed to respond strongly to a particular type of visual feature, and the convolutional layer learns a hierarchy of these features, from simple to increasingly complex as information propagates through the network. Following convolutional layers, pooling layers play a crucial role in dimensionality reduction and enhancing robustness. Pooling layers, such as max pooling or average pooling, reduces the spatial dimensions of the feature maps generated by convolutional layers. This downsampling process achieves two key benefits. It reduces the computational burden in subsequent layers, and more importantly, introduces a degree of translational invariance, making the network more robust to small shifts and distortions in the input image. Finally, to enable CNNs to learn complex, nonlinear relationships inherent in visual data, nonlinear activation functions are essential. Activation functions such as ReLU, rectified linear unit, sigmoid, or tanh are applied after convolutional pooling layers. These functions introduce nonlinearity into networks computations. These functions introduce nonlinearity into the network's computations, allowing CNNs to model intricate nonlinear mappings between input images and output predictions. With these nonlinearities, CNNs would be limited to learning only linear relationships and would be incapable of capturing the rich complexities of the visual world. The interplay of convolutional networks, pooling layers, and nonlinear activation functions is what makes CNNs so exceptionally well suited for processing and understanding image data, forming the foundation of countless computer vision applications. As the field of computer vision matured and the demand for more sophisticated and accurate models grew, researchers began to develop advanced CNN architectures. These architectures represent an evolution beyond the foundational CNN designs, specifically engineered to overcome inherent limitations and to relentlessly push the boundaries of performance in various computer vision tasks. The primary motivations behind these advancements are to achieve higher accuracy, improve computational efficiency, and enable the training of increasingly deep and complex neural networks. ResNet, residual networks, stand as a landmark innovation in this evolution. ResNet revolutionized the landscape of deep learning by effectively addressing the challenge of training extremely deep neural networks with hundreds or even thousands of training layers. The key innovation in ResNet is the introduction of skip connections, also known as residual connections. These connections allow information to bypass one or more layers in the network, creating shortcut pathways for gradients to flow more easily during training. This elegantly mitigates the notorious vanishing gradient problem, which had previously hindered the training of very deep networks. By enabling the training of significantly deeper networks, ResNet unlocked the potential for learning much more complex and hierarchical feature representations, leading to substantial performance gains across a wide range of computer vision tasks. VGG, or Visual Geometry Group networks, represent another influential architecture advancement. VGG networks, developed by Visual Geometry Group at Oxford University, are characterized by their deep and strikingly uniform architecture. The defining features of VGG is their emphasis on using exclusively small convolutional filters, especially 3x3 filters, throughout the network, stacked in deep sequences. Despite their architectural simplicity, VGG networks demonstrated that depth itself, achieved through the stacking of small convolutional layers, is a critical factor in achieving high performance. The uniform and modular design of VGG made them readily adaptable and influential in subsequent research. EfficientNet, in contrast to focusing solely on depth or specific layer types, takes a more holistic approach and to scaling and CNNs. EfficientNet's core innovation lies in systematic method for jointly optimizing three critical dimensions of a neural network: network depth, or the number of layers; network width, or the number of channels per layer; and input image resolution. By carefully balancing and the scaling of these three dimensions, according to a principled strategy, EfficientNet achieves remarkable efficiency. EfficientNet models are also significantly more parameter efficient and computationally less demanding than many earlier architectures, while simultaneously achieving state-of-the-art or near state-of-the-art accuracy on various image recognition benchmarks. This focus on efficiency makes EfficientNet particularly well-suited for deployments in resource-constrained environments, such as mobile devices or embedded systems. Let's now transition to a more recent and paradigm-shifting development. Let's now transition to a more recent development in computer vision, transformer networks. Originally conceived for natural language processing, NLP, where they have revolutionized tasks like machine translation, text understanding, transformer networks are now rapidly gaining prominence and demonstrating remarkable capabilities in computer vision. This shift marks a departure from traditional CNN-centric methods that have dominated the field for years, offering a fundamentally different way to process and interpret visual information. The central innovation driving the power of transformers is the attention mechanism. Imagine a computer vision model that can intelligently focus its attention on the most relevant parts of an image when making a decision, much like humans selectively attend to different regions of a scene. This is precisely what the attention mechanism enables. It allows the model to dynamically weigh the importance of different image regions or patches when processing the image, effectively prioritizing the most informative parts for a given task. One of the key strengths of transformer networks and a significant advantage over traditional CNNs is their ability to excel at capturing long-range dependencies within an image. CNNs, with their inherent local receptive fields, can sometimes struggle to model relationships between distant parts of an image effectively. In contrast, the attention mechanism in transformers allowed the model to directly relate any part of the image to any other part regardless of their spatial distance. The capability is crucial for understanding global context and complex relationships within visual scenes. The Vision Transformer, VIT for short, architecture is a prime example of how transformers are being successfully adapted for computer vision. VIT directly applies the core transformer architecture, originally designed for sequential data like text to image data. It achieves this by treating an image not as a continuous grid of pixels, but as a sequence of discrete image patches. These patches are then fed into a transformer encoder, enabling the model to leverage the attention mechanism to learn relationships between different paths, different patches, and understand the image as a whole. Beyond VIT, researchers are also actively exploring hybrid CNN transformer architectures. These hybrid models seek to combine the strengths of both CNNs and transformers, leveraging CNNs for their efficiency in local feature extraction and transformers for their powerful global context modeling capabilities. This fusion of approaches is proving to be very promising direction, leading to a new state-of-the-art results in various computer vision tasks and pushing the boundaries of what's possible in the field. Next, we'll be moving on to the applications and future trends. So computer vision, which is fueled by AI, is no longer confined to research labs. It has become deeply interwoven into the fabric of our daily lives and rapidly transforming industries across the globe. Let's explore some key real-world applications that highlight its pervasive impact. Considering Consider autonomous vehicles a domain where computer vision is absolutely indispensable. It serves as the eyes to self-driving cars, providing them with perceptual capabilities necessary to navigate complex environments safely. Computer vision systems in autonomous vehicles perform critical tasks such as real-time lane detection to stay within road boundaries, robust object detection to identify and track vehicles, pedestrians, cyclists, and other obstacles, accurate traffic design, accurate traffic sign and traffic light recognition to obey traffic regulations, and comprehensive scene understanding to interpret the overall driving context and make informed navigation decisions. In medical imaging, AI-powered computer vision is revolutionizing healthcare diagnostics and treatment. Sophisticated algorithms are being deployed to analyze a wide range of medical images, including X-rays, CT scans, MRIs, and pathology slides, with the aim of assisting medical professionals in disease detection, diagnosis, and treatment planning. Applications include automated cancer detection in mammograms and CT scans, early identification of retinal diseases from, from fundus images, segmentation of organs and tumors for surgical planning, improved accuracy and efficiency in large volumes of medical images, ultimately leading to the faster and more precise diagnoses and improved patient outcomes. The retail of e-commerce sectors are also undergoing a significant transformation driven by computer vision. In retail stores, computer vision powers automated checkout systems, eliminating long queues and enhancing the customer experience through seamless transactions. It also enables product recognition for efficient inventory management, visual search capabilities allowing customers to find products simply by uploading images, personalized product recommendations based on visual preferences, and in-store analytics to understand customer behaviors and optimize store layouts. For e-commerce platforms, computer vision enhances product image quality, automates product tagging and categorization, and improves visual search functionalities, leading to a more engaging and efficient online shopping experience. Agriculture is another sector witnessing a profound impact from computer vision, leading to the rise of precision farming and sustainable agricultural practices. Computer vision applications in agriculture include comprehensive crop monitoring, enabling farmers to assess crop health, growth stages, and identify areas requiring attention. It facilitates automated detection of plant diseases in pets, allowing for early intervention and targeted treatments, minimizing the use of pesticides, promoting sustainable farming. Computer vision also contributes to the accurate yield prediction, helping farmers to optimize resource allocation and plan harvests effectively, and enables the development of lab- of automated harvesting robots, increasing efficiency and reducing labor costs in the agricultural operations. Beyond these prominent examples, computer vision applications extend to countless other domains, including security and surveillance, facial recognition for access control and security monitoring, anomaly detection and surveillance footage, manufacturing quality control, automated visual inspection for defects in products and manufacturing processes, ensuring a higher quality and reducing waste, robotics, accessibility, environmental modeling, or monitoring, and many more, demonstrating the truly pervasive and transformative nature of this technology. As we embrace the immense potential of AI in computer vision, it is imperative that we confront the significant ethical considerations and challenges that accompany this powerful technology. One of the pressing concerns is dataset bias. AI models, including computer vision models, are fundamentally shaped by data they are trained on. If these training datasets reflect existing societal bias, the models will inevitably inherit and alarmingly often amplify these biases. This can lead to unfair discriminatory or inaccurate outcomes, particularly for underrepresented or marginalized groups. For example, facial recognition systems trained primarily on images of one demographic group may exhibit significantly lower accuracy or even discriminatory behavior when applied to individuals from different demographic groups. Privacy concerns are also a paramount in the age of ubiquitous computer vision. The widespread deployment of technologies like facial recognition, object tracking, and surveillance systems raises profound questions about individual privacy and civil liberties. The potential for mass surveillance, the collection of and misuse of personal visual data, and the erosion of anonymity are serious societal concerns that demand careful consideration and robust regulatory frameworks to safeguard privacy rights and prevent misuse. The increasing automation driven by computer vision and AI also brings forth more concerns about job displacements. As computer vision systems become more capable of performing tasks previously done by humans, particularly in sectors involving repetitive visual tasks like image analysis, quality inspection, and data entry. There is a potential for automation-induced job displacement in certain industries. Addressing this challenge requires proactive strategies for workforce adaptation, retraining programs to equip workers with new skills for the evolving job market, and thoughtful consideration of the broader economic and social impacts of automation to ensure a just and equitable transition. Finally, the explainability, transparency, and trust of AI-powered computer vision systems remain critical challenges. Many of the most advanced models, especially deep learning models, function as black boxes. Their internal decision-making process are often difficult to interpret, even for experts. This lack of explainability raises concerns about accountability, trust, and the ability to effectively debug or improve these systems. In situations where decisions made by computer vision systems have significant consequences, such as medical diagnosis or autonomous driving, the need for transparency and explainability becomes even more critical. The ongoing development for explainable AI or XAI techniques specifically tailored for vision models is crucial for addressing this challenge, fostering greater trust in AI systems and ensuring responsible and ethical AI deployment in computer vision and beyond. Looking towards the horizon, the future trends and research directions in Looking towards the horizon, the future trends and research directions in AI-driven computer vision are exceptionally promising and point toward even more transformative capabilities. One of the most significant trends in growing an emphasis on self-supervised learning. Current state-of-the-art computer vision models often rely on massive amounts of labeled training data, which is expensive, time-consuming, and sometimes ethically problematic to obtain. Self-supervised learning aims to overcome the limitations by enabling models to learn effectively from vast quantities of unlabeled data. These techniques leverage inherent structures and inherent structures and patterns within unlabeled data to create pretext pretext tasks that the model can learn from, effectively bootstrapping its visual understanding without explicit human annotations. This trend promises to significantly reduce the reliance on labeled data, making computer vision more scalable significantly and adaptable to new domains where labeled data is scarce. Explainable AI is another crucial, rapidly expanding research area. As we entrust more critical tasks to computer vision systems, the need for transparency and interpretability becomes paramount. XAI research in vision focuses on developing methods and tools that can provide human understandable insights into the decision-making processes of complex vision models. This includes techniques for visualizing attention maps that highlight image regions most influential in a model's prediction methods for quantifying feature importance to understand which visual features drive decisions and approaches for generating textual or visual explanations that articulate the reasoning behind a model's output. Making vision models more explainable is essential for building trust, enabling effective debugging, and improvement for ensuring responsible deployment, particularly in high-stakes applications. The future of computer vision is also inextricably linked to multimodal AI. The real world is inherently multimodal, with visual information often intertwined with other sensory outputs like language, audio, and tactile feedback. Future AI systems will increasingly integrate computer vision with these other modalities to achieve a richer and more holistic understanding of the world. For example, combining visual scene understanding with natural language processing can enable AI systems to engage in more natural and context-aware interactions with humans, understanding visual narratives and generating descriptive captions for images and videos. Similarly, integrating vision with audio processing can enhance scene understanding in noisy environments or enable lip reading capabilities. This trend towards multimodal AI promises to unlock new levels of intelligence and create more versatile and human-like AI systems. Finally, the push towards AI edge and efficient models is driven by the increasing demand for deploying sophisticated computer vision capabilities on resource-constrained devices. Applications range from mobile devices and wearable devices, embedded systems and IoT devices, and autonomous robots require vision models that not only accurate but also computationally efficient, energy conscious, and compact enough to run directly on these devices without relying on cloud connectivity. Continued advancements in model intelligence directly at the point of data capture, continued advancements in model robustness, generalization, and adaptability will also be crucial for ensuring that computer vision systems perform reliably and effectively in diverse and challenging real-world scenarios.